The new structure type aerobase superconductors with chemical formula AEA iron 4, arsenic 4 was discovered in 2016. This is basically the 122 system with space group I4MMM. Usually the dopant is substituted to the A and A site. The crystal structure does not change at all. But in some dopants with small ionic gradient, the A and A site separates and the layer stacks alternately between the iron arsenic layers. And the TC is relatively high in 31 to 36 Kelvin in 122 system. And it is remarkable that this is free of substituting a disorder in 122 system. And shortly after that, the europium containing 114 system was discovered by two groups. It shows in the circuit data superconducting transition and magnetic transition in the low temperature region. Here I show the crystal structure of europium rubidium 1144. It is regarded as the intergrowth of europium 122 and the rubidium 122 system. And europium 122 system shows two magnetic transition also SVW and near temperature. And the rubidium 1 shows the superconductivity is 2.6 Kelvin transition temperature. So in this, you can see that this crystal structure, this case also the europium and the rubidium layer stacks alternately between the iron arsenic layer as clusterographically in equivalent site. And due to the crystal structure, the rubidium doping on the europium side is just 50% whole doping, and the superconductivity appears at Tc equals 36.5 Kelvin. And the iron Mesbauer structure shows that there's no peak splitting, so there's no magnetic order in the paramagnetic state. And the Killian splitting of the spectrability of europium moment is S equals 7/2, and the Killian temperature is positive, so the dominant interaction is a ferromagnetic. And in the iron superconductor, the symmetry of the superconducting order parameter is discussed between the spin fluctuation and the orbital fluctuation. In the case of spin fluctuation, the superconductivity is induced by the electron-electron pairing of repulsive force. Due to that, the sign changes. The sign of the order parameter changes sign between the gamma point Hall film surface and the electron film surface at pen point. And this is called the S plus minus wave symmetry. On the other hand, the orbital fluctuation, the electron phonon interaction of toxos is used, but it's not a conventional one. But it uses the electron occupation fluctuation, and the sign does not change it. So this is called the S plus plus wave symmetry. So one have to use the phase sensitive law. So the inelastic neutron scattering can be one of that. So in the superconducting state, the BCS Corrin factor is applied to the generalized susceptibility. And in the case of no sign change, the Corrin factor becomes 0, so that this chiral prime, which is an imaginary part of the generalized susceptibility, is suppressed in the superconducting state. On the other hand, if there's sign change, the Corrin factor remains, so that due to the transfer of the spectral weight, the superconduction spectra is enhanced and the peak structure appears. And this theoretical study was later observed experimentally as a spin resonance mode, which was an enhancement of the chiral prime at pi pi in the superconducting state. And this pi pi corresponds to the nesting vector that connects to the gamma and the M film surface. And actually, experimentally, the Q value of 1.1 angstrom inverse observed the enhancement of the neutron scattering intensity. And the peak structure is observed in the chiral prime spectrum. So this is a non-europium containing 1144 superconductor, which was also our previous study. We observed the similar behavior of the enhancement of the neutron intensity and the peak structure of the chiral prime and the temperature dependence. So in this way, the resonance mode at pi pi is considered to be the evidence of S plus minus wave symmetry. And so motivation of our study is that what's the superconducting symmetry of European regime system, and what's the magnetic structure of European sublattice, and is spin wave excitation of the. It is important to investigate the rule of coupling between the European and the superconductivity, especially in the which has no effect of disorder due to the substitution. And the purpose of study is to investigate the superconducting pairing symmetry of iron by the neutron spin resonance by the inelastic neutron scattering experiment and the random phase approximation calculation, and to observe the spin wave excitation under Tn, and to investigate the magnetic structure of European sublattice by the single neutron diffraction measurement, and finally discuss the effect of magnetic order on superconductivity. So powder samples of this material with Hogram was prepared by solid-state reaction. The subtlety data shows that the Tc is 36.5 Kelvin and the Tn is 15 Kelvin, which was consistent with the previous reports. And the inelastic neutron scattering measurement was performed by using the Fermi chopper chopper type time of flight scattering. We used the high energy. We used the AX spectrometer at the spiration neutron source, and low energy we used the Four Seasons at JPA. So we note here that the European is a large, strong neutron absorber. So we use the simplate as shown in this photo, which is in contrast to the non-European containing material of normal cylindrical standard sample volume. And the calculated transmission is over 90% in this. So the European containing one is under 50%, even in the thickness of 1 millimeter. So this is an experimental. This is a neutron scattering intensity as a function of energy and momentum transfer for below Tc and above Tc. We can see a bright spot in the superconducting state, but this is hard to see due to the strong aluminum background. Then we have subtracted the 4 Kelvin data by the 50 data. Then the bright spot appears in the particular QE point. This is a typical behavior of the spin resonance. And constant energy cut of Q scan shows that the peak structure, peak position is Q equal 1.27 Onson inverse, which is corresponding to the pi pi nesting vector. And this is the energy scan of constant Q cuts, shows the peak energy is 70.7 electron volt, corresponding to the 5.7 kBTC. This behavior of the spin gradation and the TC is almost likely as calcium potassium 1144 and other typical iron-based superconductors, suggesting a S plus minus wave state. And we show the theoretical calculation result, the band structure and the film surface done by first principle calculations. There's a whole film surface at the gamma Z line position and the electron flame source at the endpoint, which is a typical characteristics. And the middle panel is a dynamic spin susceptibility calculated by the random phase approximation. We can see intensity around here, and this corresponds to the 0.5 Q vector, which is in good agreement with this experiment. And the energy is about 2 times delta. So delta is a superconducting gap. And we mentioned that the spin resonance is somewhat broad along the Q direction, but it is consistent with the experiment of the Q scan plot. This may be reflecting the many film surfaces with different sizes as shown in this film surface. And optical scapulometry shows that the reflectivity is nearly unity, and due to that, the optical conductivity is completely full gap suppressed, and it's a full gap behavior. And temperature dependence of the superfluid density shows the S-wave-like behavior. So the optical spectrum shows the S-wave superconductivity. So in combination, combine the inelastic Newton scattering and random phase approximation and optical conductivity. It concludes that the S plus minus superconduction pin bearing symmetry is realized in these superconductors as in other iron-based superconductors. So in addition to the spin resonance, we thought if we look for more details, the dispersions are appeared in the low energy region. So we have performed the low energy and measurement about Tn and below Tn. So first, the 25 Kelvin data, which is about Tn, the broad and quasi-elastic excitation is observed, which is a characteristic of the paramagnon and harmonic state. And cooling down below Tn at 10 Kelvin, we observe the spin wave excitation. So this spin excitation comes from the Q0. So the dominant interaction is a ferromagnetic. So what's the magnetic structure of the European sublattice in European Lobizin 1144? So first, the large aneuploid is observed during the in-plane. So in-plane is larger than the out-of-plane susceptibility. And the heat capacity measurement shows that the PKT transition. And the European Mesbauer spectra shows that the angle of the European moment is perpendicular to the out-of-plane direction. So that the European moments are confined to the IB plane. So you can say that the European moments are ferromagnetically aligned within the IB plane. So including the observation of the spin wave excitation. So remaining issue is how the two-dimensional in-plane ferromagnetic layer stacks along the C-axis. So magnetic black reflection along the 00L direction gives crucial information to address the issue. So we have performed a single crystal neutron diffraction measurements above Tn and below Tn at 00L. So this is data performed at the Senju at JPAC. First, under Tn, over Tn, 20 Kelvin data, we observe the 001, 002, 03 black peak, nuclear peak, and cooling down below TC, below Tn. The satellite peak appears at L equals 0.75, 1.25, 1.75, and 2.25 or so. And the temperature dependence of this intensity shows that it shows the evolution of the long-range magnetic order of European sublattice. And this satellite peak, the magnetic propagation vector is 0.25. So it means that the magnetic structure is a helical with 4,000 lattice. And the susceptibility data shows that the 110 direction is slightly easy axis than the 100. So the magnetic structure is like this, in plane the ferromagnetically ordered, and the spin direction is rotated to 90 degrees in the out of plane direction. So we have fitted the spin wave, and so this is a fitted obtained by the experiment, and we assume the spin Hamiltonian of this form and fitted that we obtained the JC and J1 and calculated the LSW calculation, which is in good agreement with experiment. And moreover, the Q-reverse temperature estimated from the fitted J1 and JC is 26.7 and is in good agreement with the susceptibility measurements of 23 Kelvin. So finally discuss the coupling between the long-range magnetic order of the European sublattice and the superconductivity. First, in elastic Newton scattering spectra, so there is no noticeable any change at the onset of the long-range order of 15 Kelvin as shown in this. And next, the left of superconductivity. This is highest at 36.5 Kelvin. And this is the highest among four systems. So there's no influence on TC. And no reentrant superconductivity is observed below Tn.
5 minutes.
Yes. In nickel-doped system, the magnetic transition temperature of the European sublattice is independent of the nickel content. But the TC changes and decreases rapidly. And finally, the substitution of the non-magnetic calcium, the Tn decrease, but the TC is independent. So we can conclude that the long-range magnetic order in the European sublattice plays the minor role in the superconductivity of the iron arsenic layer in European rubidium iron 4 arsenic form. So this is our conclusion. We investigate the superconductivity and the magnetism of European rubidium 1144 by inelastic Newton scattering and random phase approximation and Newton diffraction. And here we note that to our best knowledge, this is the first INS study of European containing iron-based superconductors for investigating the superconducting pairing symmetry and the possible interplay between the superconductivity and the long-range magnetic order of European sublattice. And finally, I acknowledge all collaborators. Thank you for your attention.